Welcome to the next lecture. In this lecture, I will take a little break from noise analysis and first show you something called Quadrature Amplitude Modulation. The reason is the same concept is used in noise analysis also. So I thought to first of all take this. It is in itself a very useful technique in analog communication and very useful you will see in next semester for digital communication. Right now I will do the analog communication part of this quadrature amplitude modulation, also called QAM. So what is the motivation behind this? So you can see that the DSB-SC modulation, if you see the spectrum, as we discussed this during SSB also, that we have a spectrum of 2B hertz of bandwidth, and the information contained in this right side is same as in the left side, and we motivated ourselves that bandwidth is not properly utilized. So one solution was SSB, single sideband. But we can think of another way, that instead of one message signal, suppose you have two message signals, M1 of t and M2 of t. See, if you will transmit these two message signals separately, so M1 of t, if you transmit using DSB-SC, you will need 2B hertz of bandwidth, and M2 of t will also need 2B hertz of bandwidth. But is there any way that I can transmit M1 of t and M2 of t together and use only 2B bandwidth? So that is what quadrature amplitude modulation is all about, and let's see how we can achieve it. See, we have a carrier wave, suppose cos omega ct, and what we will do usually is we would multiply this carrier signal with the message signal, right? So here is a message signal. Let's suppose M1 of t, I will multiply it here. Now see what trick I will do. We will give a minus pi by 2 phase shift to the carrier signal only. So what will we get? We will get sine of omega ct, and now I will multiply another message signal with this, and then we add them out. We use adder here. Then the resulting signal, which I will call as phi QAM of t, which is nothing but M1 of t cos omega, this signal. And now we will demonstrate that when you transmit this signal, the bandwidth is again 2B only, and we can decode both of them while transmitting simultaneously. Now see, this phi QAM at the receiver, what we first do is we will multiply it with, suppose, twice cos omega ct. Let me generate that here. So we have here cosine cos omega ct, and let me call this as x1 of t. Let's analyze this x1 of t. So x1 of t is phi QAM of t times 2 times cos omega ct, which is equal to this equation. Then we multiply this cos on both terms. Now this first term cos square we can write as 1 plus cos 2 omega ct by 2 we get, and the second term becomes twice cos theta. Sin theta is cos 2 theta. Sin 2 theta, sorry. Rearranging we get. Now if spectrum of M1 of t suppose is like this, then the spectrum of corresponding to cos 2 omega ct, the magnitude will be like this, centered at 2 omega ct here, minus 2 omega ct here, and the spectrum of M2 part is also here. There is sine, because of sine only there will be shift in the phase, but it will be again the same right here. And there is M1 of t stands here. So what can you use? You can easily use a low pass filter, and you will get, so if you pass this through low pass filter, you will get M1 of t as required. So we go back to this diagram. So here you use low pass filter, you will get M1 of t. Now again what you do is you use here minus pi by 2 phase shift, and you get twice sine omega ct. Then you multiply that also with QAM, you will get x2 of t. It is a small exercise for you. You can repeat the whole thing. So you write here, instead of cos, you write here sine. So everywhere you will get the change, so sine. So then what you will get here at the end, you will get m2 of t, and the rest will be same, only the thing is here will be m2, here will be m1. Then when you pass through low pass filter, you will get m2 of t. So we will put another low pass filter here, and we get m2 of t. So you saw that we could multiplex the signal. This is called multiplexing technique, right? So we could multiplex the two message signals, use the same bandwidth, transmit M1 and M2 in the same band, and get it received at the receiver. One of the important applications of QAM is in color television. So in color television, the information about colors can be transmitted via several messages. We can have M1 of t, M2 of t, and M3 of t. So you can multiplex and use multiple carriers which are orthogonal to each other, and do the multiplexing as you wish, and you can transmit the multicolor information in case of color television. And next semester you will see its enormous application for digital communication, and in all the next generation, including 3G, 4G, and 5G mobile communication systems, QAM is the choice of modulation, which is very effectively uses bandwidth as well as provides good data rates, which you will see next semester. Another technical application of QAM formulation is the representation of something called bandpass signal. So in contrary to baseband signal, okay, you again recall baseband signal is usually the low frequency signal. It is the actual message signal, okay. So this is the frequency response of baseband signal. Bandpass signal is something like this. Actually the name's bandpass, it comes from the bandpass filter. So the spectrum of bandpass signal is similar to the frequency response of bandpass filter, and the spectrum of baseband signal is similar to low pass filter. So hence the baseband signal is also called low pass signal. Okay, the reason is the baseband signal will easily get transmitted through low pass filter with appropriate cutoff frequency, and bandpass signal will get transmitted through bandpass filter with appropriate cutoff frequencies. Okay, so that is the reason. Now if you have two signals, let's suppose you have xc of t and xs of t. xc of t is a low pass signal or bandpass signal, sorry, baseband signal, okay, is one baseband signal, and xs of t is another baseband signal. How to represent the bandpass signal? So what will be bandpass signal? So bandpass signal will be, suppose both of them have bandwidth b, okay, this also has bandwidth b, so it is something like this. So okay, so this is spectrum. Now what you expect from bandpass signal? A bandpass signal should look like this, okay. So in other words, if you have spectrum of xc of t as suppose xc of omega, and spectrum of xs of t of xs of omega, and you want to represent a bandpass signal across some center frequency, suppose omega naught, or yes, omega naught. So you would like to get a spectrum of C of omega plus omega naught plus xc of omega minus omega naught. Now this xc and xs, they are the suppose baseband signals. Now to represent, and they have same bandwidth b. Now how can we represent them in the band pass as a band pass signal? You can think of them as a modulated signal in the same band. Okay, so think of that we want to represent them as a modulated signal but remaining in the same band. Now if you see, it is actually the QAM problem. Instead of M1 and M2, you have this XC and XS, and you want to represent them with a single signal, just like QAM signal, and they will lie in the same band. So again, hence the band pass representation will be, I will call it as band pass representation. Okay, so this will be XC of t cos omega naught t plus XS of t sin omega naught t, and I will call it X BP, X band pass of t. Now you can say that what is this? What actually, I mean, what is XC and what is XS? Actually, think of this. You will be given, suppose you will be given a band pass signal. So I will be given a band pass signal. Let's say X of t is some band pass signal. It means that if you see its spectrum, its spectrum will be something like this. It will be centered around some frequency omega naught, and maybe its bandwidth is b. Okay. Now, how to represent it component wise? So any band pass signal will have two components. One component will be, we call as in phase component. Suppose if you take this as the base signal, we call this as in phase component. And the second component, which is the sine component, so you know that sine is at 90-degree phase from the cos, and 90-degree phase difference component is also called quadrature component. Quadrature component. So this is called in phase part, this is called quadrature part. Okay, so this is the band pass representation of a signal. Now coming back to random process, suppose we have a band pass random process. Let's say X of t. X of t is now a random process, but it is band pass, means again if we see the spectrum, it will be something like this. Okay. Now we can, using the same logic, we can represent this band pass process as having two components, one cos component, one sine component. So I can write X of t is equal to Xc of t cos, suppose omega ct, plus Xs of t sine omega ct. Again you can call this as in phase component, this as quadrature component. It's also called IQ. So these terminologies will be very useful. You will see this IQ, imbalance, and all those terms in digital communication part. Now an important random process which where we will have the application of this concept is, suppose we have the white Gaussian noise, but now this process is band pass. Okay, now what does it mean it is band pass? You know this power spectral density of white Gaussian noise. Now if it is a band pass, then its power spectral density, which I will denote as Sn of omega, it will be something like this. It will be constant but over some band of the frequency, like this. This one centered around omega c minus omega c. Okay, and the height we consider as this script n by 2, this height, and this is 4 pi b. Okay, so that the bandwidth is 2b. this is 4 pi b. Okay, now let's represent the process as n of t. Now n of t is a random process which is white Gaussian noise. It is a band pass process. Band pass means it is power spectral density is not centered around zero frequency. See, if you remember last time when I showed you Gaussian noise, I showed you like this, right? It was centered around zero frequency. But practically when you modulate the signal, so your noise will also be represented in the band pass region, right? So this is that representation. And now we have to represent this in quadrature components. Now let there be two components of this noise, NC of t and NS of t. Then what is the representation? Quadrature representation. Again you will use the QAM representation. So NC of t and cos, see it is centered on omega c, so cos omega ct, plus NS of t sine omega ct, right? Now you have two components. Now these are low pass components. Remember, these are low pass, or we call them baseband noise. This is the baseband noise components. And they will also have power spectral density. Suppose SC of omega and SNC of omega and SNS of omega. Now suppose the problem is that you are given n of t, that is you are given Sn of omega, you are given the band pass power spectral density. You are required to find the quadrature components of power spectral density, SNC and SNP of omega. So how will you do that? So you will see the process. How to get NC of t? Again, go back to the QAM demodulation. So what you will do is you actually multiply n of t with cos omega ct, right? And then you pass that via low pass filter, right? So if you do that, you will get NC of t. It is very simple to observe. In fact, you will do one thing. You will multiply this n of t with, you remember, 2 cos, because if you multiply with cos, you will get NC by 2. So that then you pass it through low pass filter and you will get n of t. You will get NC of t. Okay. Similarly, you multiply n of t with twice sine omega ct, and you will pass it through low pass filter, and you will get NS of t. Now, what does it mean to multiply with? So, if you see, if n of t, if its autocorrelation function is suppose n Rn of tau, its power spectral density is Sn of omega. Now when you multiply this n of t with 2 cos omega ct, what happens to power spectral density? If you recall the formula, so Rn, this is now corresponding to NC of t. Okay, so its power spectral density will be Rn of tau cos omega c tau, right? And what will be its this power spectral density? That will be Sn of omega plus omega c plus Sn of omega minus omega c. Similarly, when you have Ns of t, that is obtained by multiplying n of t with 2 cos omega, sine 2 sine omega ct. Again, power spectral density will be Rn of tau sine omega c tau, and it will have same representation as a Fourier transform. So hence we get SNC of omega is same as SNS of omega, which is given by Sn of omega plus omega c, Sn of omega minus omega c. The low pass filter effect means that mod omega less than or equal to 2 pi b. This is when we apply the low pass filter, and it is 0 otherwise. Okay, we are not allowing other components, so we are having low pass filter. The effect of low pass filter is this thing. We enforce other components to 0. That is the effect of low pass filter. So this is the power spectral density of this. And what will be that equal to? So Sn has a value n by 2 plus n by 2 irrespective of the location, 2 pi b, and 0 otherwise. Hence that is the power spectral density of both the components is n for mod omega less than equal to 2 pi b and 0 otherwise. This is the SNC of omega, which is also SNS of omega. So this is the power spectral density of the quadrature components of noise, or in other words, a low pass representation of noise. So what will be the average power? So let's go back to power spectral density. So if you see the average power of this bandpass signal, so you know that we represent that like this: expected value of n of t square, which is also the autocorrelation at 0, right? Which is also the area under the power spectral density Sn of omega d omega, right? So here this area, we have two rectangles. We have to compute their area. So it will be n by 2 times, so in hertz, this is 2b, right, plus n by 2 times 2b, so which is 2nb. So this is the average power. Okay, average power of this band pass. And similarly, what is the average power of quadrature components? So you can say that expected value of nc square t, that again is area under the curve, but here now the area is like this. So it is 2 pi b minus 2 pi b, again it is 2b, so it is n is the height times 2b, which is 2nb for the both components. Similarly, expected value of ns square of t, that is also 2nb. So it means that the power in the baseband signal, average power, is same as the average power in quadrature components. Okay, expected value of n square of t, which is 2nb for this white Gaussian process. And this lecture is very important for understanding the next part of analysis, which we will do in the next lecture.